All right, let's dive right in. Today, we're talking about a concept from the world of self-driving cars that is both brilliant and, honestly, a little bit scary. It's called the flawless failure. I mean, really think about that for a second. Our gut tells us danger comes from stuff breaking, right? A sensor goes on the fritz, there's a bug in the code. But what if a car could be, well, perfect, operating exactly the way it was designed, and still be a major hazard on the road? That paradox is exactly what we're digging into first. We're looking at a completely new kind of danger here, one that goes way beyond a simple broken part. This is where we get to the heart of the flawless failure. So the industry has a term for this, flawless danger. Here's a perfect example. Imagine a self-driving car's forward collision sensor. It's a super bright day. The hardware is fine, the software is totally clean. But the sun glare is so intense, it shines directly into the lens and blinds it. The sensor just can't see the stopped car up ahead. See? Nothing's broken, but a really dangerous situation was just created by the system's own built-in limits. That is a flawless failure. Now, to even begin to tackle this new kind of problem, engineers had to completely rewire how they think about safety. It's a huge shift in philosophy, which brings us to our next section. For years, for decades, the main safety question for car engineers was pretty straightforward. Did we build the system right? This is the world of the classic safety standard, ISO 26262. It's all about making sure the system itself is solid. Did we write good code? Is the hardware going to last? The entire focus was on preventing the system from, breaking down on its own. But now, a new, much deeper question has popped up. It's the core idea behind a new standard called SOTIF, which stands for Safety of the Intended Functionality. And it asks something totally different. Did we build the right system? Is this system, even if it's technically perfect, actually equipped to handle the pure chaos of the real world? Is it really the right tool for the job? This new standard is basically engineers admitting, hey, we can't possibly predict every weird thing that's going to happen out there. And this table just lays it out so clearly. On the left, you've got the old way, functional safety, all about stopping internal faults, like a software bug that messes with the brakes. But over on the right, you have SOTIF. It's not worried about internal bugs. It's worried about the system's performance limits out in the wild, like a perfectly good camera that just isn't powerful enough to spot a person in thick fog. So if these failures are flawless, how on earth do you find them before they cause an accident? Well, you basically have to become a detective. Engineers are now proactively hunting for these hidden weak spots, and the way they do it is pretty cool. The first thing they're looking for is what they call a functional insufficiency, or FI for short. Think of this as the system's Achilles heel. It's not a bug, remember, it's just a built-in limitation. For instance, maybe a camera's resolution is too low to see a small animal way down the road. That's a functional insufficiency. But a weakness on its own isn't necessarily a problem. It only becomes dangerous when it gets exposed. And that's the second clue they hunt for, the triggering condition, or TC. This is the specific thing that happens in the real world, like that dense fog, or a sudden downpour, or a kid chasing a ball into the street, that makes the system's weakness actually matter. And this, right here, is the key idea. A hazard doesn't just happen because of the weakness, and it doesn't just happen because of the trigger. No, it happens right in that dangerous sweet spot, where a system's built-in weakness meets a very specific real-world event. It's like the perfect storm. To find these potential storms before they happen, engineers break the car's entire thought process into 3 steps. First, they look at the sense stage. Can the sensors and cameras be tricked or confused? Then, they analyze the plan stage. Can the car's brain, its decision-making logic, get tripped up? And finally, they look at the act stage. Are there limits to how the car can physically swerve or brake in response? And the triggers they're looking for fall into a few big buckets. You've got your environmental ones, like the sun glare we talked about. You have dynamic ones, like another car suddenly swerving into your lane. And, this is a big one, you have human triggers, like a driver who trusts the system a little too much and starts zoning out. Now, all of this gets way, way harder when you throw artificial intelligence into the mix. How do you guarantee the safety of a system that is literally designed to learn and adapt all by itself? This is what's known as the black box problem, and it is a massive challenge. An AI can learn from driving millions of miles, but you can't always see why it's making the decisions it's making. It might completely fail when it sees something it's never encountered before, a scenario its own creators never even dreamed of. This is really the cutting edge of automotive safety right now.
So, to try and peek inside that black box, engineers are using some really amazing techniques. First, you have something called out of distribution detection, or OOD. That's basically the AI's ability to say, whoa, I have never seen anything like this before. Then there's formal verification, which is super complex math used to prove that the AI's decisions will always stay within certain safe limits. And maybe coolest of all is uncertainty estimation, which gives the AI a sense of self-doubt. It can measure how confident it is, and if it's not sure, it can slow the car down or even tell the human driver, hey, I need you to take over. Okay, I know this formula looks a little intense, but the idea behind it is actually pretty simple. This is how engineers take all these what-if scenarios and turn them into cold, hard numbers. They basically multiply the chances of a trigger happening, the probability of hitting dense fog, by the system's chances of messing up in that fog. And by doing that math, they can actually try to prove on paper that a car is acceptably safe. And all of this brings us to the real goal, the new North Star for this entire safety philosophy. This is probably the most important takeaway of all. The future of car safety isn't about building some perfect, all-knowing supercomputer. It's about designing a system that is fundamentally deeply aware of what it can't do and is smart enough to either stay within those limits or ask for help when it gets in over its head. What this means is that safety isn't just a check mark a car gets when it leaves the factory. It's a living, breathing process. Cars that are already on the road will be constantly on the lookout for new and weird situations, and when they find one, they can send that data back to the engineers. This makes the entire fleet of cars smarter and safer over time. Which leaves us all with one final, very big question. And this isn't just for engineers anymore. It's for all of us. As we hand over more and more control to the machines we drive, how do we as a society draw the line? How do we decide what level of risk we're okay with? When is the system truly safe enough? It's something we're all going to have to think about. Thanks for joining me.